Local form in PLAI typed is very similar to the let form that we've implemented in our book language, in that it allows us to locally bind the name x, 10 to 10 in this case, and then we can use x in the body of the local, but x is not visible outside. So this program, of course, produces 11. A difference between let and local is that local is a recursive binding form. If I tried to let f be a function that calls f again, the f wouldn't be available. But with local, this f is bound as a recursive function, and so it can call itself. And then I can call that function with 1, which makes it go into an infinite loop, calling itself with 1. Now, infinite loops are not particularly useful usually, but the fact that we can make an infinite loop also means we can make the factorial function or the function that traverses a list and so on. What happens if you use local this way? What if we define x to be x? Because it's local, this x does mean that x, but this is a circular definition. There's no reasonable value to give x, or actually any value for x would turn out to be consistent for this program. But the language has no idea which value you might mean, and so instead it makes up one called undefined. Right? This value fits into any type, but if you try to use it, then you get a runtime error. And so it's an escape hatch for dealing with cyclic definitions like this. How about this case? Here I've defined x to be the list containing x. Well, again, this is cyclic. I don't know which x I mean here, and so there's going to be an undefined inside of a list in this case. So x will be bound to a list, that much is clear, but when we try to use x too early, then we get an undefined, and so it shows up in the list. This example illustrates that it's not that we have to use special function syntax in order to get recursive functions. Right? Here I'm defining f to be the function that takes x and calls f to x, and this will be an infinite loop just as it was before. The reason this works is because lambda delays the evaluation of the body, and it turns out we don't try to use this particular f until we're already down here when we call the function f, which calls the function f, and so on. So the key thing to making these recursive function definitions work is this lambda delaying. Okay. Instead of writing local, from now on I'm going to write letrec, which has the same shape as our let form, but the rec, of course, means recursive binding. So here again we've got an f that recursively calls itself and goes into an infinite loop. What if I use letrec with f on a list containing a function? So f now stands for a list whose only item is a function. If I pull that function out and call it on x, then that is calling the function itself again. Similarly, if I take it out at the first place, call it with 1, this will be an infinite loop with calling the function calling itself with 1. So again, it doesn't need to be a lambda right after f. The key thing is that the lambda here delays the use of f until it has been, where it does have some definition. So let's suppose we want to add letrec to our book language. Now, since we don't use x on the right-hand side here, this program should work out and should give us 11. And our first attempt to implement letrec might just lean on the letrec of PLAI typed, as we've done so many times before. And that would mean that as we interp the right-hand side, we do so in an environment that's extended to have the name that we are trying to bind. And the value that we put there, well, we just refer back to the value which is the result of interp. And then as we interpret the body, the plus expression, we again extend the environment with the binding for x back to the value. And this one will all work. In fact, we will get 11 back. But it turns out the reason it worked is we never actually referred to this use of val. We had a second use of val over here that was delayed to inside the letrec. If we change our example to the function example that calls itself, and we try this same pattern, we interp the right-hand side, which is a lambda expression, in an extended environment that binds f to val, this val gets evaluated too early, and it will be undefined. And when we later call the function, even though we bind it again to a value that does refer to a function, the closure that we get back from this lambda interpreted will refer to this environment, which has the bad value inside of it, the undefined value, and you end up getting a runtime error saying that you're trying to use undefined when you wanted a closure. So our very first attempt to use Letrec to implement Letrec did not work out, and the key problem here was that we evaluated val too early. There was nothing to delay the use of this val. We built up the extended environment before we called interp, which then saved that environment. So this is the val that we want to delay, and so we can use our delaying technique, which is to wrap a lambda around the val. So I've changed this to be a Letrec with two bindings. They're mutually recursive bindings. And that way I just construct the new environment once, and I can use it down here. It's a simplification over the previous part, and we do that because now our environment is going to work. This use of val, even though it's defined later, is delayed, and then we have a lambda in our interpreter, which again doesn't go try to use the val, it just remembers this extended environment. And so by the time we get down here, val has been defined as the closure. And when we call this function f and we pull out the environment and we look up this val, we get the closure back like we wanted. To do this, we need to change bind so that it has, instead of a symbol and a value, it has a symbol and a function that returns a value. So we change binding this way. Instead of value here, we wrap it with an arrow. Right, there are 0 things before the arrow, so that means a function of 0 arguments that returns a value. And now when we're in lookup and we find the name that we're looking for, we pull the value part out of a binding as we did before, but now that's not a value yet, it's a function that produces a value. So we add an extra pair of parens that call the function and give us the value back that we wanted.